Hello, and welcome to this part where you will get questions and answers regarding lectures 3 and 4. First question. Suppose that you train the logistic regression classifier on a dataset of patients diagnosed as either having diabetes, this is class 1, or not, class 0. And now given a new patient, your model predicts this, 0.6. So how do you interpret this prediction? The answer is B. So the estimated probability that the patient X has diabetes is 0.6. So the output of a logistic regression model, which depends on parameters theta, when we say that this is equal to, for example, 0.6, then this is the probability that the predicted class is 1 given the patient X, and also the parameters vector theta. Second question. Which of the following cost functions is minimized by a logistic regression model? And here we are talking about a non-regularized logistic regression, and that's what we studied so far in lecture 3. Later in the course we will see a regularized version of this, but here we are talking about the one we studied in lecture 3. The answer is A, and this is just the cross-entropy cost function that we saw in the lecture. And h of x, this prediction, is just the sigmoid of theta transpose x. Now, if you look at answer B, this is wrong. This is not a cost function. This is just this part here. It's just sigmoid of theta transpose x. And sigmoid of x is also wrong. This is not a cost function. And if you look at C, this is the mean squared error, right? But if your h of x is defined in this way, it's the sigmoid of theta transpose x, then this function here becomes a non-convex function. And that's why we preferred to use this one, because this one is a convex function. It has just one global minimum. Question 3. Which of the following is true? There is just one correct answer. The correct answer is A. So logistic regression and support vector machines, SVM, are both binary classification methods. Now these two are binary classifiers, but they can be used for multi-class classification if we apply some strategies like those that we saw in some previous lecture. The one versus all strategy and the one versus one strategy. So for example, this one allows you to train, if you have C classes, then you will train C binary classifiers, one for each class, right? If you want to apply it for multi-class classification. And in this case, you will train one binary classifier for each pair of classes. So this is in the order of 2 to the power of C classifiers. But originally, if we talk about one logistic regression and one support vector machines, they are binary classifiers. They work with two classes. If we check the answer B, neural networks are used for classification only, not for regression. This is wrong. They can be used for both classification and regression. If we check C, decision tree and k-nearest neighbors are both binary classification methods. This is wrong. They are naturally multi-class classifiers, so they can directly be applied to a data set where you have more than two classes. Here, the random forest and logistic regression are both multi-class classification methods. This is wrong. It's correct for random forest because random forest is just an ensemble of decision trees. So it can be applied to any number of classes. But as we said previously, logistic regression is a binary classifier. Now you are given a simple data set which has 4 data points, so 4 rows, and 2 columns, meaning 2 features. And you are also given the corresponding outputs, the labels. So for this first data point, this is the corresponding label, positive label. For the second data point, this is the corresponding label, and so on. So this first feature is called x1, right? And the second feature is called x2. And now the question is, in which of the following feature spaces is this data set linearly separable? You can try to draw those data points together with their labels on a piece of paper and then see which answer is correct. There is just one correct choice here. And the correct answer is C. So in this feature space and this one, the two classes are linearly separable, but not in the first one. So if, for example, we take the first feature space, x1, x2, so we have those two features, x1 and x2, and we try to plot those data points together with their labels. So if we take the first data point, this one, so it is at the position -1, -1, and it has a positive label. So it lies here with a positive label, plus. If we take the second one, -1, +1, and it has a negative label. So it is here with a negative label. The third one is here and it has a negative label. And the last one is here and has a positive label. So in this feature space, these two classes are not linearly separable. You cannot draw a line which perfectly separates those two classes. But if you do the same thing and draw the other feature spaces, you will see that in those cases, the classes are linearly separable. Now consider this very simple data set. If you normalize this data using the min-max scalar, then what will be the values of the first feature? So based on that, you will just subtract the minimum value from each of those values and divide by the max minus the mean. So basically you will find that the feature values becomes this, right? So the correct answer is A. Now read this description and select the correct answer among those. And the correct answer is B, because as we saw in the lecture, you can create additional polynomial features and add them to your data set. You can create them based on your two original features. And so you will get a higher dimensional space. And then by training a linear regression model in this high dimensional space, you will get a model which is nonlinear in the original space. So it's basically a polynomial model in the original feature space. Now, given these two pictures of two models, A and B, select the correct answer among those. The correct answer is C. So model A is likely more accurate than model B on new test data. Because if you look at model B, it correctly classifies all the training examples. So it achieves zero error basically, but it only works on this training data. So this is a case of overfitting. And model A will probably generalize better to new unseen data. Now suppose that you are given a data set of n data points and two features. So for example, this data set, and you have two classes, the positive and the negative class. And you are also given a point called C, right? And what we want to do is to learn an unknown radius R, right, of the circles centered around C, such that this circle separates the two classes with a minimum error. So to do this, you need to find the parameter R that minimizes some suitable cost function, right? So E of R, this cost function depends on R. So our parameters that we usually call theta are now called R. This is just one parameter value, R. So the question here is, how would you define or design such a cost function? So there is only one parameter R, right? C is given to you. And you want to design the cost function E of R that we can later minimize in order to find the best value of R. So think about it and try to write it down. There is not only one solution, but try to come up with any reasonable cost function for this problem. Okay, one way to think about this is the following. So let's say that we pick a positive example. So if the label of the example is positive, so it belongs to the +1 class, then we have two cases. So the first case is, let's say that we picked this data point. So the distance between C and X is larger than R, right? So this is the difference. So here the distance between X and C is larger than R. And the other case is the other way around. So this is when the distance between X and C is less than R. For example, this is the case for this data point. So for this second case, this is fine because this means that the distance between C and X is less than R. This means that X is within this area, so it's fine. So in this specific case, our loss will take 0. But in the other case, we should have a penalty because this data point is far away from C. So the distance exceeds R, and this is the difference. So let's say that in this case, we penalize our cost by this amount. So this is our loss, this difference. And you can do a similar reasoning for the case where the label is -1. So you take an example of a negative example, right? And in this case, it's fine if the distance between C and the data point exceeds R. So it's the inverse of this. But if you get a data point like this one, a negative data point, where the distance to C is smaller than R, then this is not good. So in this case, we should penalize our cost. And based on this reasoning, we can write all this in a more compact way based on, for example, this cost function that I defined here. So for example, if we are talking about a positive example like this one, so in this case, y will be positive. And if this example has a distance to C which is larger than R, then this quantity here will be positive. And the maximum between this and 0 is this, and that's what we want. Well, we want to penalize our cost based on this difference. So this corresponds to the first case here. But if we are at this second case, we don't want to penalize our cost, right? So the difference here will be negative, right? So the maximum between a negative number and 0 will be 0, right? And so on. And then we have just the average of those losses. So that's one way to define such a cost function, but there are many other ways. Now suppose that you fit a decision tree classifier of depth 10 to a dataset, and then you see that the accuracy on this dataset is 100%. So you basically have 0 error on the training dataset. Now consider the following points and select the correct option among those. The correct answer is A. So depth 6 will have a higher bias and lower variance compared to 10. And that's because with a smaller depth, we will have a simpler decision tree model. So this is a less complex model. Okay, so for example, with depth 10, you achieve 0 error, 0 training error. So maybe you are overfitting. And then in this case, you have a very complex model. So you have a high variance and low bias. So with a smaller depth, you will get a simpler model, which means you are increasing the bias and decreasing the variance, right? In which machine learning problems do we use decision trees? The correct answer is D. So a decision tree can be used for classification and also for regression. For classification, it's called usually a decision tree classifier. And for regression, it's called a decision tree regressor, or sometimes a regression tree. So please check lecture 4 for more details about this. Read the description and select either true or false. The correct answer is A. So yes, a decision tree can be represented as a set of rules. So for example, this prediction here, this part can be presented as if the latitude is larger than 20 and the month is between 4 and 8, then predict class, the positive class, and so on. Read this description and select the correct answer. The correct answer is B, because if we are at a given node, meaning some region of the feature space, and all the data in this region has the same label or the same output, then we don't need to split this region again into more subregions. We can just create a leaf node that predicts this output. If a decision tree T1 has a lower training error than another decision tree T2, then T1 will always have a better test error than T2. Is that true or false? That's not necessarily the case, so the correct answer is B. Because you can imagine that, for example, T1 is overfitting, maybe it has very high depth, and then it achieves a low training error on the training data set. But then when you apply it to new unseen data, then maybe it will achieve a poor performance. Which of the following is true about decision tree? The correct answer is B. The model complexity increases with the depth of the tree. So if you have a decision tree which is not deep, for example, the depth is just 1, then this is a very simple decision tree. It cannot create complex decision boundaries. But if you increase the depth, then the model or the decision tree becomes more and more complex. The answer C is not correct because the model becomes simpler when you set the minimum leaf size to a larger number, because then you will split less. So for example, if you say that the leaf size cannot be smaller than 500, this means that you will not split it anymore when it reaches this number 500. So you will get simpler decision tree. And A is also wrong because when the size of the training dataset is small, then you are more likely to overfit. But if you increase the size of the data, then this does not generally affect the complexity of the model.